Welcome back to Accredited Laboratory. Today, we're exploring one of the most exciting frontiers in modern science, how artificial intelligence is transforming analytical chemistry. From chromatographic optimization to real-time data interpretation, AI is rapidly changing how we work, think, and even make scientific decisions in the lab. Let's understand what this transformation really means, and how it can impact your analytical workflow. Artificial intelligence, or AI, refers to computer systems that can perform tasks requiring human-like intelligence, learning, recognizing patterns, and making predictions. In analytical chemistry, AI doesn't replace the chemist, it enhances their capabilities. Machine learning, a key branch of AI, learns from experimental data such as chromatograms, spectra, and calibration results, and then predicts outcomes like retention time, peak shape, or even compound identity. Imagine training an AI model using hundreds of LC-MS runs. The system learns the patterns and can predict how a new compound might behave before you even inject it. Analytical chemistry has become data-rich but time-poor. Each LC-MS or GC-MS run can generate thousands of data points. Manually reviewing and validating them takes hours and introduces subjectivity. AI tools can automatically clean, process, and interpret data, turning days of manual work into minutes. Instead of manually optimizing dozens of chromatographic conditions, AI can predict the best mobile phase composition or gradient time based on previous experiments. So, how does AI actually do this? Let's look at some key algorithms. Several AI and machine learning techniques are now part of analytical workflows. For example, neural networks can predict chromatographic behavior, while SVMs can classify unknown compounds by comparing fragmentation patterns. In many labs, PCA and clustering algorithms already help in chemometric analysis, allowing scientists to visualize trends or detect adulteration. Let's look at how AI is practically applied. AI models simulate chromatograms and predict retention behavior. This minimizes trial runs and solvent use, saving both time and resources. AI helps differentiate between noise and true peaks, predict fragmentation, and classify unknowns using deep learning. In omics studies, deep learning automates peak detection and biomarker discovery in complex LC-MS datasets. Spectroscopic fingerprints analyzed using AI can reveal food adulteration, for instance, distinguishing authentic honey from syrup blends. AI offers significant benefits: faster analysis, improved reproducibility, and smarter decision-making. But it also brings challenges, like the need for large, high-quality data sets and the black box problem, where it's hard to explain why AI made a specific prediction. Despite these challenges, AI's integration with digital tools is paving the way for the next big leap: the autonomous laboratory. We are moving toward laboratories that think and learn, systems where robots handle samples, AI selects optimal parameters, and data is analyzed in real time. In this digital ecosystem, AI is not just an analytical tool, it's part of a smart lab network, integrated with IoT, LIMS, and cloud computing. AI is no longer a futuristic idea, it's an essential partner in modern analytical chemistry. If you'd like to explore more about today's topic, here are some key references. Thank you for watching Accredited Laboratory. If you found this lecture useful, please give it a like and share it with your lab colleagues. In the next episode, we'll dive into how machine learning models are reshaping LC-MS, MS, and GC-MS data analysis. Subscribe to stay updated. And remember, in science, innovation never stops.